Hi, I'm Ishan, and this is an 11-chapter series on static program analysis. Static program analysis aims to determine possible behaviors of programs, and it's called static as opposed to dynamic program analysis because we're going to determine these properties merely by looking at programs without running them. This first chapter will be all about how static analysis powers tools you're familiar with. We'll talk about the fundamental limitations of static analysis and how designers can work around these constraints. Static analysis has been around since the 1960s, where it made its start in optimizing compilers. An optimizing compiler might ask a static program analyzer some questions about the code it's looking at in order to determine whether a particular optimization is possible to make. We'll talk about a few questions it might ask here. So first up, is a function f reachable from main? If a function isn't reachable from main, we can eliminate it from the code. This is called dead code elimination. Can an expression being computed inside a loop be moved to outside the loop without changing the behavior of the program? If so, this is an optimization we might want to make. Instead of computing something many times, we'll just compute it once. This is called loop invariant code motion or code hoisting. All right, LICM for short. Does the value of a particular variable depend on the program's input? If it doesn't, we can just compute this value ahead of time when we're compiling the program and save some time when we're running the program. This is called constant folding. We might ask ourselves what are the lower and upper bounds for a particular variable, and this might inform the way we represent this variable during the runtime. Do pointers p and q point to disjoint locations in memory? If so, we can use parallel computing to speed up operations on them. This is called aliasing analysis. Aside from optimizing compilers, static program analysis provides value to correctness analyzers. A correctness analyzer might take in as input another program and be able to answer questions like the following. Is a null pointer ever dereferenced? Do you ever divide by 0? Is there ever any arithmetic overflow? Are variables ever read before they're initialized? Are arrays always accessed within their bound? Can there be pointers to areas of memory that have already been freed? Does the program terminate on every input? More questions we might ask ourselves. Are all assertions guaranteed to succeed? Is a particular type of exception ever thrown? Can input values from the users flow unchecked through core paths of the program? Can secret information become publicly observable? In the context of parallel programs, we might ask ourselves a few more questions. Do two threads ever access the same resource without proper synchronization? Can a part of a program deadlock? Static program analyzers also power IDEs. They answer questions about the program like, where is this particular function being called from? Where is this particular function that we're calling defined? At what parts of the program could this particular variable have gotten its value? This might be useful, you can imagine, in debuggers. What is the type of a particular variable? If you've ever used OCaml, you know that you don't have to define the types of your variables explicitly, but if you hover over a variable, your IDE can tell you what type OCaml has determined this variable is. Our dream as static program analysis scientists is to be able to take in a program and determine many of these interesting properties about them. Unfortunately, we're not going to get them. That's due to a result from 1953 called Rice's theorem. Rice's theorem states that all non-trivial semantic properties about a program are undecidable. By non-trivial, we mean that it's neither true for every computable function nor false for every computable function. We can see Rice's theorem hold true if we consider the special case of the property, does a particular variable have a constant value k throughout the execution of a program? For starters, suppose that Tm of j simulated the jth Turing machine on empty input. Now suppose we fed into our program analyzer the following program. X equals 17 if Tm of j x equals 18. Clearly, if simulating the jth Turing machine halts, then x will not have a constant value, but if it never halts, it will. So we've just created a decider for the halting problem which is an undecidable problem. So that means that this kind of analysis can't exist. As static program analysis scientists, we get around this problem by providing instead approximate answers. Approximative analyzers can give us answers for most programs, although not all. Since we have approximate answers, we will have some errors in our answers, but it's good if all of these errors lean to the same side, and we call these conservative approximations. For example, one conservative approximation of how much memory a program uses might always overestimate the amount of memory being used, so it'll never report something lower than what is actually used. A program analyzer is called sound if whenever it provides a result, it is correct, but it doesn't have to provide results for all programs. It might instead provide maybe as the result, or I don't know. Trivially, a conservative approximation that is sound might just say, I don't know, for all program inputs, but this wouldn't be very useful. In this last section, we'll talk about the impossibility of building a program analyzer that can determine if a program will fail, even if you know for a fact that the program will terminate. In a later video, we'll learn about abstract interpretation, which is a mathematical framework for reasoning about these approximations. We'll show this by modeling programs as Turing machines with a special fail state, and a program is set to fail if upon completion of the Turing machine is halted in its fail state. We'll show that no such program analyzer can take in one of these Turing machines and determine if it may fail when executed by way of contradiction. So let's say there was such a program analyzer, and let's call it P. P takes as input a description of a Turing machine and accepts it or rejects it depending on if the input may fail when executed. So if P accepts the program, that means it will never fail. If it rejects it, that means that it may end up in its fail state for some input. Given P, we'll build a new Turing machine called M. M is going to take in as input a Turing machine T, and as an intermediate step, create a new Turing machine called S. S is a Turing machine that simulates T with T as input for at most the size of T steps. So T is encoded in some way, and in the encoding, T has some size. Let's call it size of T. And the thing about S is that S will fail if and only if T simulated on T for at most T steps ends up in an accept state. Lastly, M will take S, feed it into P, our program analyzer, and if P accepts S, then we will accept T, and if P rejects S, we will reject T. And now we'll do our usual trick of inputting M into itself. So what does it mean to input M into itself? Well, M gets fed in as T, and we're constructing this S out of M. So S is a program that runs M with M as input for at most size of M steps. If M accepts M, that means that S will end up in a fail state, and that means P will reject it. But that means that M would reject M. But if M rejected M, S won't end up in a fail state, and P would have to accept it. So this clearly isn't possible. And one thing to note here is that the programs are passing into P never diverge, because by definition they just stop after the size of the program steps. So even despite this restriction on what we're passing into P, we still know that P can't exist in this context.